How do you know if you can attend every meeting on your schedule? Meeting Rooms is a Pattern Mastery 100 favorite and a classic warm-up at Google, Amazon, and Meta for interval reasoning and sorting. Over 25% of candidates miss subtle overlaps or forget to handle back-to-back meetings. Master this.
Unlock a whole world of scheduling and interval-based interview questions. Let's break down Meeting Rooms using the basic approach, a reliable method for interval overlap problems. You're given an array of meeting time intervals where each interval is start, end. Determine if a person could attend all meetings. List of intervals, unsorted, each as start, end. Boolean, true if you can attend all meetings, false otherwise. Imagine planning your day with back-to-back meetings. Can you get to everyone without running late? Interviewers might ask, how would you quickly check if any two appointments on your calendar overlap? What's tricky? Input can be unordered. Meetings that end exactly when the next starts do not overlap. Only need to find one overlap to return false. First, sort all intervals by their start time. Then, walk through the sorted list. For each meeting, compare its start to the previous meeting's end. If the current meeting starts before the previous one ends, there's an overlap, return false. If you make it through without overlaps, return true. Let's clarify. Sorting is critical. Unsorted input can hide overlaps. Edge cases. One meeting, always true. Empty list, true. Edge cases. Empty list, true. Single meeting, true. Overlapping at end. 0, 30, 30, 40, no overlap. Sort intervals by start time. For each meeting from the second onward. If interval I0, less than interval I11, overlap, return false. Time complexity for this approach is O(n) log n, dominated by the sorting step. We use a method called sort and check overlap. First, we sort all meeting intervals by their start time. Then we walk through the sorted meetings one by one. If any meeting starts before the previous meeting ends, that means there's an overlap, and the person cannot attend all meetings. If no overlaps are found, the schedule is conflict-free. Simple and clean. In our Java implementation, we start by defining the solution class. This is just where our function will live. The function can attend meetings returns true or false depending on whether someone can attend all their meetings without overlaps. We first sort all meetings by their start time. Think of it as lining up events from earliest to latest. This makes it easy to see if any of them collide. Next, we loop from the second meeting onward so we can compare each meeting with the one right before it. At each step, we check, does the current meeting start before the previous one ends? If yes, there's an overlap, and the person can't attend both. If we find such a conflict, we immediately return false because the schedule is impossible to follow. If we finish checking everything without finding a single conflict, we return true, meaning every meeting fits perfectly with no overlaps. And that's how this algorithm works. It first sorts all the meetings to create a clear timeline, then checks each pair to detect overlaps. Efficient, simple, and elegant. Sorting the intervals takes O(n) log n, which dominates the runtime. After sorting, checking for overlaps is O(n). This makes it extremely efficient for detecting schedule conflicts and one of the cleanest interval problems to explain to beginners. Now we test our can attend meetings function with a sample schedule. Input intervals are 0, 30, 5, 10, 15, 20. Each subarray shows a meeting start and end time. The algorithm sorts meetings by start time and checks for overlaps. If any meeting starts before the previous one ends, it returns false. Here, meeting 2 starts at 5, before meeting 1 ends at 30, so there's an overlap. Output is false, confirming the function works. The implementation efficiently detects overlaps and ensures the schedule is feasible. Time complexity for this approach is O(n) squared because we compare every pair of meetings. We use a method called brute force pairwise check. For each meeting, we compare it with every other meeting. If any pair overlaps, the person cannot attend all meetings. If no overlaps are found across all pairs, the schedule is conflict-free. This is the simplest solution, but also the slowest. In our Java implementation, we start by defining the solution class. This is where our function will live. The function can attend meetings returns true or false depending on whether all meetings can be attended without overlaps. We first store the number of meetings in a variable called n, which makes the code easier to read. Then, we run a loop picking one meeting at a time, thinking of it as choosing a meeting to compare with others. Inside that loop, we run a second loop, comparing the current meeting with every meeting that comes after it. This avoids repeating comparisons. For each pair, we check if the two meetings overlap. If meeting I does not end before meeting J starts, and meeting J does not end before meeting I starts, then the meetings overlap. That means a conflict exists. If we detect any overlap at all, we immediately return false because the person cannot attend all meetings. If we finish checking every pair and find no overlaps, we return true, meaning the schedule works perfectly. And that's how this algorithm works. It loops through every meeting, then compares each one with all others to see if any overlap. Efficient for understanding, simple to write, and elegant in its clarity, though not the fastest. This approach checks every pair of intervals, which is why the time complexity is O(n)². It's easy to understand and implement, making it great for beginners learning overlap logic, but inefficient for large inputs. Let's see how our solution checks meeting intervals and determines if all can be attended. Input intervals are 7,10, 2,4. Each pair shows a meeting start and end time. The algorithm compares each pair of meetings. If any meeting starts before the previous one ends, it overlaps and returns false. Here, 7,10 and 2,4 do not overlap, so the function returns true. Output is true, confirming the implementation works. The method efficiently checks for overlaps, handles all cases, and ensures accurate results. Let's wrap up the meeting rooms problem. It's one of those deceptively simple scheduling questions that interviewers love, and it quietly tests your logic around sorting and interval overlap. Miss a single detail, and you'll end up double-booked. Breakdown recap. We're given a list of meeting intervals, each with a start and end time, and we need to determine if a person can attend all meetings without any overlaps. If any two meetings overlap, the answer is false, otherwise, true. Assess recap. The key insight here is that meetings can come in any order, and back-to-back meetings are allowed. So, we first sort all intervals by their start time. Then, we walk through the list, comparing each meeting's start to the previous meeting's end. If a meeting starts before the last one ends, we found an overlap and can immediately return false. If we reach the end with no conflicts, we return true. Structure recap. Our structure is simple. Sort the intervals by start time. Loop through each one, checking for overlap with the previous meeting. If none are found, return true. Edge cases like an empty list or a single meeting automatically return true since there's nothing to conflict with. Implement recap. We implemented the sorting and single pass check using built-in functions, quick, clean, and efficient. When we ran it on LeetCode, the solution executed smoothly without any errors. Check recap. We tested multiple cases, including overlapping and non-overlapping intervals, and all returned the expected results. The time complexity was O(n) log n. For sorting, with only O(1) extra space. Closing insight. The big takeaway? Sorting is your best friend in interval problems. Once your data is ordered, detecting overlaps becomes a simple linear scan, turning what looks complex into something elegantly straightforward.